So today what we're going to do is look at higher order derivatives, and that just means the second derivative, the third derivative, and the fourth derivative, and so on. So higher order, well, let's just start with second derivatives. So if the derivative of a function is f prime of x, the second derivative then is the derivative of the first derivative. And so it is denoted by f double prime. And the third derivative then is going to be denoted by f triple prime. And then you can keep continuing on this process and go, as far as you want. But after the third derivative, they use this notation instead. So there would be the fourth derivative. Here's the fifth. Or if we want the 9th or 10th or 30th, then we just show it like that. Okay, well, let's take a look at this one. Find the first 5 derivatives of our function here. So our first derivative is going to be 8x cubed minus 6x. Our second derivative will be the derivative of that. So 24x squared minus 6. Our third will be 48x. Our fourth will be 48, and then our fifth would be 0. So polynomial functions are fairly simple to do. Let's find the third derivative on this function, and then after we get that derivative, we want to substitute in a 2 and for the t. So our first derivative then will be negative 4t cubed plus 6t squared plus 1. Whoops. I don't know why I wanted to put an F there. Our second one will be negative 12t squared plus 12t. And I want to do it F again. And then our third is negative 24t plus 12. So now if we substitute in the 2, we get negative 48 plus 12, which would be a negative 36. So notice how when we're working with polynomials and we do the derivatives, like when we're finding higher order derivatives, you notice that each successive differentiation, the degree of the polynomial drops by 1. So eventually, higher order derivatives of polynomials then are going to degenerate to a constant function. So let's take a look at this here. Polynomial functions, however, are the only functions in which we will eventually get a constant function. For any other function, successive differentiation never produces a constant function. Okay, so let's try that then. So let's go to this screen. Find the first 4 derivatives of y is equal to x to the negative 1. All right, so our first derivative let me get rid of that arrow. Whoops. Oops, I lost that. And I went up to another one. Let's see, let's come back down here, see if I can find that one. Here we go. So the first 4 derivatives of y to the negative 1. So we come up with negative x to the negative 2. The second derivative, positive 2 x to the negative 3. Third, negative 6x to the negative 4. and the fourth is 24x to the negative 5. So you can see on this one then, we are not approaching 0, and it's just going to get uglier and uglier every time we do another derivative. So here is a non-polynomial function, excuse me, and notice that once again the derivative is not approaching a constant function. Okay, so now let's take a look at an application. So the velocity of an object moving in a straight path is given by the derivative of its position function. Alright, so if we know the position, so like if we're throwing a ball up in the air and we know we have this equation that gives us the height of it or its position, the rate of change of that function will be the first derivative, and that is going to give us the velocity. And then if we look at the rate of change of the velocity function, then we're looking at the acceleration of the object. So the position function is like your original function, so that would be f of x. The velocity would be the first derivative, and the acceleration would be the second derivative of the position function. So if we have to find any one of those at a particular time, then we substitute that whatever we want for the time into the appropriate function. So if I want to know what's the velocity at time 3, then I have to do the first derivative and substitute in the time into that. If I want to know what's the acceleration at a particular time, then I do the second derivative and substitute in the time into that function. So let's take a look at this. I took this from section 2.3, and it talked about the general position function for a free falling object, and it gave us this. And if you go back to the that podcast, you'll see this. And in this particular equation, the v sub o stands for the initial velocity, and the h sub o stands for the initial height. So if they give us that information, then we can plug it in to get our general position function. And the derivative of that then would be the velocity function. So if I do the derivative the way it stands, I would have negative 32t plus v sub o, which is the initial velocity. And then the absolute value of that is the speed of the function. Okay, so on this problem then, we have a ball. It's thrown into the air from the top of a 160-foot cliff, and then we're given the initial velocity, and we want to find all three, the height, so we'll have to write that equation then, and the velocity, and the acceleration. Okay, so let's start off with the height. So remember, I'm going back to this screen here, and that's the equation that we're taking. Negative 16t squared plus v sub o plus h sub o. Okay, so let's go back to this screen. And we want the position function. So we could say the height of it, and I want to make sure it's in blue, is equal to negative 16t squared. The initial velocity is 48, so I'm going to plug in that 48 for the v sub o. So plus 48t, and then the h sub o is the initial height, so we have 160, so plus 1, well, I don't know where that point came from. So ignore that point, and I'm afraid to, there we go. So that's just plain 160. All right, so I'm going to go now do the velocity. So the velocity is the change in the height. So I do the first derivative. So that first derivative is negative 32t plus 48. All right, and then I'm going to do the second derivative because the change in the velocity is the acceleration. All right. So now we're going to go back up and we have to substitute in the t is equal to 3 into each one of those. So on the first one, you're substituting in a 3 here, so negative 16 times 3 squared plus 48 times 3 plus 160. And when you simplify that, you get 160. And that's the height of it, that's the position of it, so that's 160 feet. All right, now we're going to plug in the 3 into the first derivative, or the velocity function. And when we simplify that, we get a negative 48, and that's the change in the feet with respect to time. So it's negative 48 feet per second. And then in the acceleration one, we don't have a variable to place the t in, so it is simply, whoops, better grab the black, negative 32 feet per second squared. So that's your acceleration. So it just depends on which derivative you need, but we can still plug it in. So it's fairly simple doing those second derivatives, and you'll just have to practice with some different kinds of functions. So hopefully you'll do well with that. I don't think there's anything else you need to know. You should be able to catch on fairly quickly. All right, see you in class.